going to use at the front end in a rename stage to allow us to change from an architectural register number that the programmer used to the physical register number that's going to hold the result of the instruction that produces that register. And the idea is, by doing this translation, by using a new register to store the destination of every instruction as we rename them, we eliminate all of the false dependencies. There's no output dependencies or anti-dependencies. The only dependencies we're left with are the true dependencies. And so when we rearrange instructions, we'll rearrange them according to that true dependence order. In order to do the rearranging, we introduced an RS, which is reservation stations. On the block diagram we looked at before, when I had one up for the Pentium 3, or if you look at Intel's block diagram for like the core, they'll call this the scheduler, but traditionally it's called the reservation stations, because that's what Tomasulo called his when he implemented out of order back in the 60s. And this is going to store the information that we need to determine if the instruction is ready to execute. And so we have an opcode. We have a couple source register numbers. We have the values for those. Maybe the physical register number that it's assigned to, and I think when we were looking at it, we were adding just a single bit to allow it to check to see if the instruction was ready. Basically, the instruction is ready once it has the values that it needs, the source values that it needs to compute the operation. And so we might have an add that is waiting on a particular physical register, but it might have the value for some other operation. And so it's not ready yet because it's waiting on physical register 10 to be produced by some other instruction that's executing in the processor at the time. So our instructions wait in the reservation stations until they're ready to be sent to the functional unit, the ALU, or the memory, or whatever unit that that type of instruction requires, the branch unit for branches. Any quick questions up to this point? So we talked about the general approach that we're going to fetch and rename the instructions in the original program order and stick instructions into the reservation station in that original program order. And then they're going to get issued out of the reservation stations to the functional units in some true dependence order. And then we talked about, eventually, we're going to have to put them back into order for things like branch mispredictions and cache misses. So the structure to do that is called the reorder buffer. And I'm going to show it in the simplest approach. And I mentioned before, there are more than one kind of design decision that you could make, an approach that you could take to implementing out of order execution. But it's easiest to kind of start with the most straightforward. And so we might implement our reorder buffer as a circular queue where we have a pointer to the oldest instruction in the processor, and then we have another pointer to the youngest instruction in the processor. If we use this kind of approach, notice that our physical registers are really just part of the information that's stored in the reorder buffer. So when we rename the instruction, we'll be assigning it a location in the reorder buffer. And because of that, even an instruction that doesn't necessarily write a physical register still needs a location in the reorder buffer. It may not write a physical register, but we need to keep track of it so that we can then commit that instruction. And so when we commit an instruction is when it becomes architecturally visible. Meaning it's visible to the user, to the programmer. So the kinds of additional information might be the architectural register that instruction is going to write. When we're executing the instruction, we don't need to know what architectural register is going to write. We only need to know the physical register that was going to write. But when we're going to commit it, when we're going to make it visible to the user, we need to know what was the register name that the user used. We need to know if the instruction's done. So when the functional unit, maybe this is an adder that produced this value, when it stores it in the reorder buffer, we need to mark that that is complete. And so it's ready to be committed. And so we're going to store the instructions in the original program order. Remember I said when we rename the instructions in the original program order, we're going to assign them a location in the reorder buffer sequentially. So we keep all the instructions in order, and then we're going to commit them to architectural state in the original program order. And so we would commit it by simply writing the destination to the architectural register file and then moving our pointer. So we'll take this value, and we'll store it in the architectural register file, and we move the pointer so the new oldest instruction is here. And so that part's pretty straightforward. One of the downsides of this approach is that there is a lot of copying. So we're going to have this bus that goes from your reorder buffer to the architectural register file. And if we want to be able to execute 3 instructions per cycle, we have to be able to fetch 3 instructions per cycle, rename 3 instructions per cycle, and then how many instructions do we have to commit every cycle? At least 3, right? Because we don't want to have a bottleneck, because if it's 2, then we're only going to be able to sustain 2 instructions per cycle. So we want to be able to commit 3 instructions per cycle. Why do we commit them in order? Because maybe we have a branch. And the branch was mispredicted. And we have some other instructions that are finished. They came after the branch because remember, these are the instructions sequentially. Maybe this was a subtract and it's done. Maybe we have some other one, it's not complete. that bit's a 0 and this bit's a 1 to indicate it's complete or not. So we could have a mix of instructions that are completed and not completed. If the branch is the oldest instruction in the reorder buffer and it was mispredicted, that means that these instructions should never have been fetched. So we executed on the wrong path of our program. We predicted taken when it should have been not taken. So when we have a misprediction, what did we do in the in-order case?
Flush.
We're going to flush the pipeline. Now we have instructions in that in-order case. The instructions never actually wrote their result that came after the branch. They have written a physical register, but they are not committed to the architectural register yet. And so we're going to have to do what with all these instructions? If this is a branch that's mispredicted,
Flush them.
we're going to have to flush them. And we can clear them out of the reorder buffer. We can clear them out of the reservation stations because these instructions are not in the reservation station anymore because they're already finished. This instruction's not finished yet. It might still be in the reservation station waiting for its functional unit so that it can execute. So we'll have to clear all the instructions out of the reservation stations and all the pipeline stages that are in order that come before then. When it's mispredicted, then we know what the correct program counter should have been for the next instruction, so we can start fetching the next instruction. So it's relatively straightforward as far as throwing these instructions away, clearing out the instructions in the reservation station, flushing the instructions in the pipeline stages that are in order, and then fetching the correct instruction. What about the register alias table? So these physical registers correspond to instructions that are in the reorder buffer that came after the branch. For now, we're assuming the branch is the oldest. What do we need to do to the register alias table?
Do we have to back it up?
Well, if we think about, if we're going to flush all these instructions, where are the good values for, register 1, register 2, register 3? They're not in any physical register because we're flushing those. Where are they? When the instruction finished, like the instruction that came before the branch, it copied its value to the architectural register file. So the good values are all in the architectural register file. So if we have a branch, so we'll say so we're going to, if it's the oldest instruction in the reorder buffer and it's mispredicted, we're going to flush all the instructions that we fetched, and we're going to reset this so that each one just points to the architectural version of that register. So that the next instruction that we fetch, well, it'll get the very next available physical register. And it'll read the sources from the architectural registers because this represents the state as of the program, right as of the instruction that was the oldest, the last one that was committed.
So we do that to the whole graph then?
Right.
Every register.
When we have So the nice thing about the reorder buffer is that since it keeps all the instructions in the original order, if the branch is the oldest, we know that everything to the left, everything that got fetched after the branch is speculative and on the wrong path, and we can throw it away, which means everything in the reservation stations and all the renaming that we did was bad, and we have to just go back from scratch and start over. But it guarantees that we have, the precise state as of the point of the branch, because it's in the architectural register file.
So when things are moving out of this reorder buffer, do they get stops at the non-complete instructions?
Yes. So if the oldest instruction is not ready to be committed, we have to commit them in the original program order, and so then we would stall. But it shouldn't directly impact performance until the reorder buffer completely fills up, because we're still executing instructions. It's just that the commit has stalled. I mean, it will impact performance because you won't be able to commit, you won't be able to have a sustained 3 instructions per cycle committed, but it won't actually stall the execution until the reorder buffer fills up.
That makes sense.
But when we do fill up the reorder buffer, the renaming would stall because we wouldn't be able to assign a physical register to an instruction. So we wouldn't be able to rename it. This instruction is going to do an add, but we don't have anywhere to put its result until we commit something and start filling it up. So what might cause the reorder buffer to fill up? Say it's 128 instructions.
Cause it to fill up, I guess, if something took a really long time to complete. Is that
Yeah, so what might take a long time to complete?
like a miss?
Yeah, so if we have a load that misses to main memory, that load may take 100 cycles, and so if we're adding 3 instructions per cycle to the reorder buffer, 128 divided by 3 is a weird number, but whatever that is, it's 30, 40, it's 40 cycles, right? So 40 cycles of not completing anything, it's going to fill up, and then we're stalled. But if it takes less than that, if it took 20 cycles, we might fill up halfway, and then we'll start to drain it out.
Okay, so once it fills up, how do you kind of get out of the hole? Like, if you know what I'm saying, is there a way that this will move faster than the instructions executing?
It will be. It will in that the instructions that are being committed, we can commit 3 instructions per cycle even if they were originally dependent on each other, because all we're doing is copying a value from here to some register. And so even if this was an add that produced a value and this was a subtract that used that value, that doesn't matter anymore. They're both done. We know the results, and so we're just copying the results to the destination. And so we should be able to sustain a 3 instruction commit as long as we have instructions that are completed. Where here we're depending on the dependence order, and so if there's not 3 per cycle, then the reorder buffer should sort of catch up. Branch mispredictions will allow it to catch up because we'll kind of reset everything from scratch. And so, obviously there's some thought that goes into the sizing of this. Probably the biggest challenge is just the larger you make it, then the slower the access time is. And so most modern processors, it's about 128 physical registers, which means, as long as it hits in some level of the cache, it probably won't completely stall, but if it misses to main memory, it's going to cause a stall eventually. But the idea, you're hoping that you're getting some useful work. If this head is a main memory miss, you're still doing 127 other instructions. You hope that those are useful instructions, and maybe some of those are also cache misses, and so you can do them in parallel, so that by the time the oldest one is done, some of the other ones are done as well, and so things then move faster. Similarly, if the oldest instruction in the reorder buffer had caused an exception, we would do the same thing that we do for a branch misprediction. We'd flush the instructions that came after it, This guarantees precise exceptions because all the instructions that came before the exception have written the architectural register file, but none of the instructions that would come, all the instructions that came before the instruction that caused the exception have written the architectural file, but none of the instructions that came after it have.
So also, did we say that the architectural register file is totally separate from the physical register file? Like there's actually two different.
In this approach, yeah.
Okay.
In the
Because
simple
if it wasn't,
approach.
that would mess things up, right? Because we would have already written to the architectural registers or something.
Yes. We'll see that another approach where we kind of decouple the physical register file from the reorder buffer is to just use physical registers to hold the architectural registers, but we'll need to keep track of which physical registers hold the last committed version of each architectural register. And so as long as you can keep track of it, then you can throw away all the other physical registers and just keep those. So, reorder buffer, it puts all the instructions back in the original order. It guarantees precise exceptions because we know the ordering of the instructions. We know that once the instruction is the oldest in the reorder buffer, everything that came before it has already been committed and has affected architectural state. There's another part of architectural state, though, in addition to the registers. What's the other part of architectural state? What's the other part of your program state, in addition to the registers? Your data is not just in registers, it's also in memory, right? So what does that mean for stores that are going to change memory in an out-of-order processor? Can a store, say this is a, it's back one. Say this is a store and it's got its value. I don't know, you stick it somewhere. It's going to store a 0. It's actually got a value and it's got an address, right? Once we have the address and the value, can we actually write memory? No, because what could happen to this store? It could get flushed, it could get squashed. And so we have to actually wait until the store is the oldest instruction in the reorder buffer so that we can commit it in the original program order. And so committing is also going to be writing to data memory. And so then we'll have to talk about, we're going to be actually loading, once we have the address computed for loads, we want to do that load as soon as possible because that load probably feeds a store, probably feeds a add or subtract or multiply or something else. We can't wait for every memory operation to do them until they're the oldest in the processor because we wouldn't do much out of order. So the loads are going to access memory way back here, but the stores aren't going to write memory until the very end. And so what are we going to have to do with these writes in between? They're not going to write to memory yet, but they're going to have to write somewhere that the loads could see them. And so we're going to have some kind of buffer, basically, to buffer the stores until they get to the point where they can be written to memory. Before we talk about that, for both the exceptions and branches, I made this assumption that the branch was the oldest in the reorder buffer. What is the downside of waiting until the branch is the oldest in the reorder buffer? What if this had been a branch that was mispredicted? Or, say sorry. I'll leave that there and you can just use your imagination. What if in here there's an instruction that's a branch that's mispredicted? If I have to wait till it becomes the oldest, then there's some wasted cycles when I knew it was mispredicted, but I didn't do anything about it until it got to this point. Why did I assume that the branch was the oldest when I did this? Because it still needs, yeah, if it's not the oldest, then I have kind of two classes of instructions. I have the ones that came after that I want to flush. I don't need their state, but I have the ones that come before. They haven't been committed yet, but I'm not going to flush them because they came before. And so it's complex if I have a branch that's sort of in the middle of the reorder buffer. If I know it's going to be mispredicted, it's complex to do the flush when it's not the oldest, because I'm going to have to basically reset the register alias table to the architectural registers, and then I'm going to have to process the instructions in the reorder buffer, sort of renaming them again, so that I can get what the rename state was at the time that I fetched the branch or renamed the branch. Because I really want to go back to the wrap value at the time that the branch was renamed, so that I can kind of undo the stuff that came after, but not have to redo the stuff that came before. And so that's kind of the trade-off in terms of the simplest thing is to wait, but that may hurt performance because it's possible that I have 126 instructions that I'm going to have to wait for them all to complete before I do anything about this branch misprediction. I can detect that it's a misprediction as soon as, if it's a branch equal, as soon as I have the two values, I can compare them and I'll know if I predicted taken and they're actually not equal, it should have been not taken. It's a misprediction, but doing something about it may take some complexity in going through the reorder buffer and processing it to do the updating of the rat to get it to the point that it matches what it was when that branch was renamed. Similarly for exceptions, maybe for exceptions it's okay because I'm not as worried about the performance of exceptions. Maybe it's okay to wait till the exception is the oldest, but that could be a long time. I could delay exceptions quite a bit, so maybe it's better to take them right away, and if this instruction causes an exception, process these so that they're allowed to finish before the exception is actually taken. Probably for exceptions, you just let stuff that came before the exceptions finish so that it became the oldest before you flushed. But for branches, you may not want to, because you're going to have mispredictions pretty often, and it may hurt performance. Do you have a question, or? Okay, looks like you have a question.
So, for the reorder buffer, when
Yes.
are instructions entering this? As soon as the next instruction in program order hits the reservation station, then it jumps into here?
As soon as they're renamed. So
As soon as they're renamed? then
when they're
they-
renamed, they're going to be given a physical register, and that's going to be its location in here.
So they're immediately,
Yeah, I mean, the timing of when you write the info in here, maybe it's the next cycle or whatever, but the location for that instruction is assigned at rename.
so essentially shouldn't that just fill all the way up, like at the beginning, because the order of it? It's not, because it's not waiting for the reservation stations, because they're either complete or not complete. So wouldn't it just fill up if it already knows the instruction program order, or maybe I'm just not?
Well, but instructions are going to be finishing out, they'll be executing out of here, and so the first ones you rename are going to be the first ones in here. So hopefully after a couple cycles, the very oldest instruction should be finished, if not a couple of them. And so things should start. I think it should be big enough that it doesn't just immediately fill up. And usually your reservation stations are going to be much smaller than your reorder buffer because this is more complex, because remember, these source registers are actually comparators that are comparing with the register number of everything that's finishing. So maybe, an aggressive out of order, this is 32 entries, but the reorder buffer is like 128 entries. And so you might stall putting instructions into the reservation station because there's no reservation station to put it in. Or you might stall putting it into the reorder buffer, depending on which one filled up first. Similar, like the same kind of example, if I have a load that missed all the way to main memory, if I have 32 instructions that depend on that load, they'll all get stuck in the reservation station, nothing can go. The hope would be that some of the instructions are independent of the load and they can go ahead and start, they can go ahead and execute and complete. They just can't commit until the load commits first. So I mentioned stores. At the very least, even if we're not going to be super aggressive with loads and stores, we need to buffer stores so that when the stores have their address and their data, they can write that data into a buffer, and subsequent loads can access that buffer to see if the data that they need to load has been written by a store that has not yet been stored out to memory, not yet committed. So maybe I have a store in here somewhere. Oh, this one. It's complete. Its data is 0. Its address was A00. It's a store. If I now have a load in my reservation station and it loads from address A0000, this instruction has not committed yet. And so if I went and looked in the data cache, the value for this instruction has not yet been stored. So it's not going to find the data that it wants there, but if it looks in the load store queue, it can see, oh, there was a store that came before me that stored to the same address that I stored to. So it's going to have to search older stores to see if it's an address that matches. So the loads and stores in the load store queue are in the original program order, so they get added to the load store queue either when they're renamed or when they get stuck into the reservation station, because they have to happen when we still have the instructions in the original program order. And so again, we have another thing that can fill up. If I do a lot of loads or a lot of stores, I may have the load store queue full. This store is going to leave the load store queue once it's actually committed, and the value for that store is reflected in the data memory. Questions about that one piece? Now, what if I had some loads that came after? Okay, if I've got a load to the same address, it's going to forward. So I need to be able to do that. So instead of getting the data, instead of this load getting its data from memory, it's going to get it from the store that's in the store buffer. But what if I have some other loads? Oh, maybe this is unknown, sorry. Maybe this load I haven't computed the address yet, but this one I have. If this load is in the reservation station and it's got its value, maybe its value is 0. It's ready. If this load hasn't yet finished, can I do this load? Can I do the loads out of order with respect to each other? I should be able to, because even if this load loads from the same address, it's going to get the same data, but it's not going to change what the data is at that location. Now, once we start talking about multi-processor architectures, we may have issues of consistency, where other threads may expect to see this load happen before this load, and if they happen in a different order, that could change the values so that we get a result that we might not expect, but not necessarily incorrect. And so we'll talk about different consistency models and what that means about reordering memory operations.
So would other cores have access to the same load store queue?
They would not, because this is pretty much a pipeline structure that occurs and keeps track of the stores that have been entered into the reservation station. Maybe they have computed their address and computed the data that they're going to store, but not yet been committed. So they're very tight into the processor core. And other cores are probably going to have their own like L1 data cache even. And so this is really changes to the, the stores or changes to the data cache that haven't happened yet, but should happen. And since they're in here, we could flush it. If this branch was mispredicted, we'd flush this store. All the stores that are here are going to get flushed. So reordering loads, doing a load that comes after, that's something that should be pretty safe to do because loads don't change program state. What if I had, instead of forwarding a load, what if I have a store well, let's see here. What if I have a store that's storing, okay. What if I have a store that's going to store to this address, but we don't know the data yet? So the data is coming from R5, and R5 is coming from a multiply, and it hasn't finished yet. So we have the address, not the data. If a load comes after it, loads from the same address, can we do this load? We know that this load depends on this store, and so we know that this load needs to stall. It needs to get its value from forwarding once the store actually has its value. What about this load? Again, when we talk about memory consistency, reordering loads and stores will be an issue that may change the consistency model, which again may not be a problem or it might be a problem. Basically, the more reordering we do, the more relaxed the consistency model is going to be, and maybe the weirder it's going to be for people that are programming on these multi-core architectures. When it's a super relaxed model, things might happen in a weird order that they don't expect, and they just have to learn to put serialization in to make their programs work. But most people don't know how to program multiprocessor stuff, and they throw, if their code doesn't work, they throw synchronizations in until it finally works. So eventually they'll figure it out. as far as a single-threaded program, this load is accessing a different address than this one. It should be okay to do this load before this store, right? We're going to throw it away if this, if this store causes an exception or some branch misprediction happens. We're not going to commit its result to the register file until it's the oldest instruction in the processor, and so all these other instructions would have to finish. We know that the addresses are different. It should be safe. But it does require that we have the loads in the load store queue, and we can search to see older stores to see if all the older stores are to different addresses. So, we talked about a couple cases. Loads reordering with loads, seems like we pretty much want to do that, otherwise we're going to have pretty serial execution in our out-of-order processor. Loads reordering with stores to known addresses. Should be safe program-wise. We should get the same answer that we would get if we didn't reorder them. But there may be some consistency issues if we have a multi-processor thing with shared memory. What if instead of the thing being unknown being the data, what if the thing that's unknown is the address? So it's going to store a 0. These loads are loading A000, C000. Are they going to get the value forwarded to them from the store? We can't tell at this point, right? Because this store, maybe the address is computed with the add and it hasn't happened yet. Maybe maybe the input to the address computation depends on another load and it missed in the cache. And so we're waiting on that. We know the data is a 0, but we don't know what the address is. Can we reorder these loads in that store?
What if they read from that address?
Right. So if we want to be super aggressive in terms of the out-of-order execution, it'd be kind of nice if we could do the load. We already have the address. It'd be kind of nice if we could do the loads, because otherwise we're going to have to stall them. What do you think the odds are that they are loading from the same address that this stored?
Well, one of them's not.
One of them's not, right? The odds are probably pretty good that they're not loading from the same address. And so the third case would be loads reordering stores to unknown addresses. Say we go ahead and do the load. We're going to get some values from memory. Eventually, say we got a 7. Eventually, this store is going to have its address. When we commit this store, we're going to write to the data cache at address A0000 a 0. What else do we need to do when we commit this store? Is it enough to just update this load? Why not?
Because it affected other instructions.
Yeah. This load, wrote physical register, whatever, physical register 27. Maybe there are other instructions that were in the reservation station. They were reading register 27 and they executed also. And they got 7 instead of 0.
So you have to flush them.
So you really need to flush all the instructions because you did a load, gave it a stale value, and then you let stuff that came after the load execute with that stale value. And so in order to know that you need to flush, what do you have to do? When you commit the store, you have to look for younger loads that have already loaded and loaded from the same address. And if they match, well then you did this load in the wrong order. The load really needs to happen after the store because they're to the same address. And you did the load early. And so then you have to flush. But you can kind of treat it like a branch misprediction. If you flush from the store, you could flush all the instructions that came after the store. You could reset the wrapped to the architectural register file, and then just fetch the PC for the instruction that comes immediately after the store. And that would be safe. It turns out performance-wise, it is beneficial to reorder loads with stores, even if it's a store to an unknown address. It turns out that luckily for architects, okay, so we have this relationship. If this was a store to an unknown address, if we always reorder loads that come after with this store to an unknown address, we're sort of predicting something. What are we predicting? We're always predicting that loads that come after store are independent. But one of the big tools that architects have is prediction. We could come up with another way to predict that the load is independent of the store. The simplest is to simply say, if I ever flush because of a store that a load gets reordered with, then I'm going to record that store's address in a table, and I'm never going to let loads reorder with that store again. Because it turns out there are very few instances where we're going to have to flush, but if this is in a loop, if I do have to flush once, I'm probably going to have to flush every time through the loop, because I'm going to do the same mistake over and over again. But if I remember not to do it again, then it won't flush.
How would we get the address of the load for the store? Like, how would it compute?
Because maybe we had code that was like, load word, this, and then we're going to store something to the thing we loaded. And we're doing a load. So this store is going to be blocked by this load. We don't know the address for this store till this load finishes. And maybe this is a cache miss, it goes to memory. But it's possible that R3 just happens to have the same address in it that R1 is going to have. And so, maybe in our program, maybe we have like an array where we have the index that's computed somehow, and maybe we have it on the left-hand side and, in a different computation on the right-hand side. But it turns out that, for some values going through that array computation, they're both accessing the same index. And so it's definitely possible that we don't know R1, but we do know R3, and so we'd like to go ahead and do the load. But if we do that, then, of course, we're also going to want to do the next thing, which is going to be some add. And as soon as we pollute R9 with a stale value, then the next instruction is going to pollute R10 with the stale value. And we sort of lost track of what's good and what's bad, and so we're going to flush and we're going to start over. So the simplest approach would be to just record stores that you could have a simple table where you store the addresses of stores. The cause flushes because it's going to be a small number, because most of the time the code doesn't do this. If there's a store to R1, most of the time if the load is going to be the same address, it's probably using the same address computation, and so if this was stalled, then this would be stalled. But sometimes it does happen in real programs. That simple approach, there are definitely better approaches, approaches that work better. I may have told the little anecdote about it's the University of Wisconsin Alumni Foundation versus Intel lawsuit. Have I mentioned this before, maybe in an undergraduate course, if you had me there. So, professor from the University of Wisconsin comes up with a new idea. He's gonna he publishes a paper in a conference with a way to predict whether a load depends on a store. Goes and talks at Intel, here's my slides. It's a great idea, you know, we run benchmarks and we show that it's better than the simple table approach. Because that one, you know, you miss some opportunities because you're never gonna move a load around this store. Maybe it's only gonna flush once, and you always are gonna at least flush once every time, and your table's small, maybe, you know, you have to evict things for the table. So they come up with a better approach and they say, oh yeah, we filed for a patent, you know, here's our patent number, blah, blah, blah. So what does Intel do? Well, they put it in every processor they make, right? Don't bother to license the patent, they just put it in all the processors.
What year was this? Or just
Not too long ago, I don't know. I do know it's Wisconsin Alumni Foundation, which is the holding, like here we have the OU Foundation, which owns the patents so that because like state agencies can't sell things. So like we can't sell a patent, but the private OU Foundation can sell the patent. So it's 2008. And so I had seen I'd seen the settlement estimated at like $1 billion. So you could look it up. It was see here, there's a news story. They then turned around and sued Apple and won, but then that got overturned because Apple uses Intel processors, right? So they're selling something that violates their patent. But they basically got a certain number of dollars for every processor that Intel sold from that point on, and you know they sell a lot of processors, so it's a lot of money. So you know, if you come up with a cool idea, you know, OU does patent research, so you know we could patent it, and then you know, if Intel had licensed it, they would have licensed it for like hundreds of thousands of dollars, not billions of dollars. But you put it in there, and then they say, well, this is worth $4 every chip, and you know, I've sold 250 million chips, and so that's $1 billion. So you know, you can look up the University of Wisconsin's algorithm for predicting whether loads and stores conflict, but it's this is the idea. We have a store that comes earlier in the program. We don't know what address it's going to store to. We have a load that comes later. We do know its address. We want to go ahead and let it read from the cache. But if we do that, we're then making the prediction that the load is going to read from a different address from the store. When the store commits, we have to search the load store queue for all the younger instructions to compare the address that we eventually store to see if any of them matched. And if they did, then we have a problem and we have to flush. So, you know, we can do out of order execution with any of these models. The original Tomasulo approach didn't reorder loads and stores at all. They didn't have to worry about branches. You know, we would like to go all the way to being able to rearrange loads with stores, even if they're to the same address, and even if they're to an unknown address. Obviously, if we know that it's the same address, we're not going to reorder and know that we're causing it always to flush. We want to reorder loads with loads. That's even like, you know, minimally rearranging memory instructions. But we're going to revisit this when we start talking about consistency, because if we have shared memory variables in a multi-threaded program, the other thread will be able to see the order that we load and store things. And so that may, like I said, give unexpected results if we allow a processor to do memory operations in an order that's different than the way that the programmer wrote them. So when we talk about multiprocessor, a lot of what we'll talk about is coherence. So if we have a shared memory location, just making sure we agree on what the value is, and then consistency, which will be if we have a shared memory if we have multiple shared memory locations, making sure we all agree upon sort of the ordering at which those shared memory locations are updated. And you know, the more relaxed we are, the better the performance, but then maybe the harder to program. So that's probably a good natural stopping point. We're going to pick up on Tuesday and talk about some alternatives. We'll say, okay, we always talked about one reservation station. Tomasulo actually had separate reservation stations that are immediately connected to the ALUs. And so they're smaller, but they're, you know, by the time it's in a reservation station, it's just waiting for one ALU.
So what time do we have outside tomorrow?
Well, I said